Hi everyone, thank you everyone for coming in today. We have around 30 people so far in the session, expecting around 50 today or more. So just going to give about a minute or so before we get started. If you do have any questions, please feel free to message it in chat or the QA section or raise your hand and we'll get to your question. Okay, I see around 36. Okay, I think we can get started.
All right.
Okay, yep. So today we have Michelle who's going to be presenting the topic of updating a BAS or building automation system for optimized heat pump performance. So on the next slide, we do have a ISO, the Save on Energy Managers Playbook. It's basically a podcast with bite-sized episodes of 18 to 20 minutes, and it basically features real-world stories and then Ontario's energy market industries, any challenges people have faced in the energy industry, and so on. So please feel free to check that out. It's in Apple Music, it's in Spotify, and any of the major platforms. And I'll pass it on to Michelle.
Thank you very much. So good morning, everybody. So today we're going to talk about heat pumps and BAS. We're going to do a quick introduction, obviously, on heat pumps. I know it's going to be quite familiar to most of you because the type of heat pumps you have will obviously have an impact on how you optimize your BAS. It will impact the number of sensors, the type of sensors you have. So it's obviously something we need to be very familiar with. Uh, we're going to talk a bit about FDD and heat pumps, even though FDD can be applied to any HVAC systems that you have. We're going to discuss specifically what it can do for your heat pumps. And at the end, if I'm not too long, there should be time for some Q&As. I'll let you read the objectives on your own once you get the slide deck. So let's start right away. So BAS and heat pumps. Obviously, if you want to get the most of your BAS, you need to integrate the heat pumps into that BAS. And it seems almost a normal thing to consider, but I've seen many installations where the BAS was not, sorry, the heat pumps were not integrated in the BAS due very often to compatibility issue. Just an example, the older VRF systems, not the newer one, but the older ones, they were not BACnet compatible or BACnet compliant, so they could not be integrated, which led to obviously, I won't say inefficiencies, but less efficiency out of the system. And once you have your heat pumps integrated into your BAS, you can actually start considering advanced control strategies, which actually that little graphic you see on the screen is one of those advanced controls. It's not something that you do at first when you have a heat pump in your building. You really need to take, I like to say, baby steps to control your heat pumps, to optimize your heat pumps, and you can go to those more advanced strategies. But there are things that need to be there right away, which is, it talks here about demand flexibility. And we'll see that one of the things that your BAS should, I'm going to say must, but unfortunately it's not always the case, should have, is live data on your building total demand so that you can actually control the demand for your building. Because once you've got heat pumps, you've done a step towards electrification. And one thing that can really handicap you on an economic fashion is what happens to your demand once you've got those heat pumps installed. So it should really be there. Um, and the one thing that you need to keep in mind is that heat pumps are usually way more sophisticated or complex machine than what you typically have for, let's say, heating. It compares to obviously your chiller in terms of complexity, but they're more sophisticated machine. You need more points, and your control sequence needs to be adapted to take into consideration those complexities, how the performance of those machines will vary based on the outside air temperature, for example. So those things need to be considered. Quick review of the type of heat pumps, and that's, I know it's quite basic, but just so we speak the same language. We'll divide the heat pumps here in 4 different categories, which will impact how your BAS needs to be optimized to use those heat pumps to the most of their efficiency. So you got the air-to-air heat pumps. The first term and the second term, air and air, always refer to the source and the sink. So where is your heat pump in, let's talk heating mode, is taking its heat from, and where is it putting the heat in? So obviously an air to air heat pump is very common. That's what you have in most residential applications. Those mini split systems, those rooftop units are air to air. You get the air to water heat pumps. Again, it's using the air as its source. And that's always very important, because as soon as you've got an air source heat pump, you know you will be very often limited in terms of how that heat pump can work under colder temperatures. When you get to the water-to-water heat pumps, very often, but not always, you actually don't necessarily have that constraint, because you can use whatever that water source is in terms of where you draw that heat, is not necessarily directly impacted by outdoor air temperature. It can be, but it's not always the case. And again, it will impact how you control that heat pump. And because it's also having its sink as water, so it's a hydronic heat pump, it will, as we will see, impact how you can control your supplemental heating, which is actually very different than what you can do when you have an air-to-air heat pump. So all of those, even though it looks very theoretical, they do have a direct impact on how you will modify the control sequence in your BAS, because it will impact how you control based on outside air condition, as well as how you control your supplemental heating, because a lot of those heat pumps, maybe other than the geothermal one, will typically need to have some supplemental heat. And then you also have the water to air heat pumps. You can think of your distributed water source heat pumps, which is fairly common in many buildings, where the source is a water loop that can have a boiler and a cooling tower, and its sink is the air, because the DX coil, the direct expansion coil, sends that heat when it's in heating mode directly into the building air, not through a hydronic loop. Just a word, heat recovery chillers per se are not heat pumps. They don't have a reversing valve. We'll see that there are some heat pumps that we call heat pumps that always work in only one mode, which could be typically the heating mode. They're still heat pumps. They have the possibility of providing both heating and cooling, whereas a heat recovery chiller is just a chiller where you use the heat. So it's not considered in this presentation as a heat pump, even though in fact you can almost use it as such. Quick review, we said air-to-air heat pumps, most common, package heat pumps, where you will often have supplemental heating. That's natural gas. There actually are incentive programs for those. Like I said, you program that into your BAS, you integrate that into your BAS. You want to make sure you know how that heat pump capacity and COP varies with outdoor temperature. It can be quite important to know that, especially if you want to calculate how much savings you're going to get before you actually integrate that into your building, integrate that into your BAS. You can use a tool like Red Screen, which will provide you that kind of high level estimate, but you need to have a curve like you see on the slide that will provide you an estimate of how much you're going to lose in terms of capacity as the temperature goes colder, and how much you're going to lose in terms of coefficient of performance, COP. Mini split heat pumps are very similar, but obviously they're split, and they usually don't have integrated supplemental heating, whereas the air-to-air rooftop unit will have integrated supplemental heating. And we're going to talk about the importance of integrating that control into your BAS rather than just using the onboard controller. That's where the integration part will provide you more benefit than if you try to use only the onboard OEM controller for those type of heat pumps. The other one that is getting more and more common, but obviously is less common than the air-to-air rooftop units, is the central air source heat pumps. Those heat pumps can provide either heating or cooling through a hydronic loop. It's often used for heating purposes, where you still have a chiller that provides cooling. So it's a heat pump that can actually work in a single mode, but it can work in both mode and provide your building cooling. But it is one at a time. It does not do simultaneous heating and cooling. It is air source. Therefore, just like the one we saw before, you need to know how much capacity it's going to lose with outdoor temperature getting colder and what's going to happen to its COP, because that is something that needs to be considered when you will program how your supplemental heat will work on your BAS, and again, needs to be integrated into your BAS. Quickly, cascade heat pumps. It's really a chiller, and you have a heat pump to boost the heat. And that's one of those applications where the heat pump is really just used in heating mode. It's for buildings where you want to use that rejected chiller heat, but you need higher temperature. So it it's a heat pump, but use only heating mode. I'd say it's probably the least frequent one we see of the ones that I'm presenting right now. If you've got a central ground source heat pump, this is typically water to water. It can be water to air, but typically will be water to water. This is the one type of heat pumps where when you integrate it into your BAS, it's unlikely to have supplemental heat, but it's not impossible depending on how the system was sized and the temperature levels that you will require. But typically, what you want to make sure, again, is to have that integrated properly into your BAS, because the performance of that system will be highly dependent on how well you control the supply water temperature in that loop, because those type of heat pumps can be what we call distributed heat pump, where you're going to have heat pumps in all the spaces, or it can be a central heat pump where you will have a hydronic heating loop and a hydronic cooling loop linked to a big, large central heat pump. So you got those two types of configuration for ground source heat pump. The distributed heat pump is what you see here. Those distributed heat pump system are actually, it's an old system, very conventional, where you have water source heat pumps in all of the different spaces, which take their energy out of a common water loop, which can be conditioned by a boiler and a cooling tower. For those of you who have those systems, that boiler is a nice place to retrofit with a heat pump, an air source heat pump, to replace that boiler, or at least to be in parallel to that boiler, because this loop is a low temperature loop, which is perfect for a heat pump. So again, if you integrate that into your BAS, you would be able to obviously optimize the use of your air source heat pump that will replace that boiler, or that will supplement that boiler, or vice versa, I should say. And it could also be a ground source heat pump, in which case you likely will not have a boiler as a supplemental. All your heat will come from the ground source. In the BAS, this loop temperature, as I said before, is your critical item. You want to make sure you control that properly. And those water source heat pumps, they do have range. If you want to use a lower temperature for ground source heat pump in that type of loop, you need what's called an extended range water source heat pump. So if you've got already a heat pump in your building and you say, I'm going to go with a air source heat pump, but I'm going to drop the temperature so that I can, use that heat pump more efficiently, you may hit a wall here, because your water source heat pump may not have the range to be able to use a cold source. So you got to make sure you know what type of systems you have before you start considering it, and before you start reprogramming, obviously, your BAS. The last one that I'm going to talk about, actually, it's not the last one. There's one more. It's the VRF. VRF system, or variable refrigerant flow systems, they are heat pumps. There's two types. There's heat recovery systems, which are typically what we call three-pipe system, and there are purely heat pump system. When you have a VRF, that's a heat pump only system, all your interior units are either in heating or cooling. In a few years ago, those systems could not be integrated into a BAS, which was kind of a pain, because you ended up with two different control systems. Now, VRF systems typically have BACnet compliant controllers. So you want to make sure that if you get a VRF system, it is BACnet compliant if you have a BACnet BAS, so that you can actually integrate that properly into your system. If you've got a heat recovery type VRF. It's still a heat pump, even though the term heat pump and heat recovery might be confusing. It's still a heat pump, but it does allow simultaneous heating and cooling of the different units that are inside the building. And they're obviously typically air to air, but just so you know, they also make hybrid VRF, where the interior system is hydronic. So you have less refrigerant going through your building. It does, again, have an impact on how you integrate that into your BAS. The last one, which you may not have seen very often yet, maybe so, is an air source heat pump or air to water heat pump that's called a four pipe heat pump. So it's basically kind of a heat recovery chiller, but designed as a heat pump where you will have two hydronic loops, a chilled water loop and a hot water loop linked to those air source heat pump. And they can provide either full heating, full cooling, or they can also be in heat recovery mode. So it does sound a bit like a VRF system, but it's fully hydronic. And again, those are air source, and it's quite important to know that because when you integrate into your BAS, you need to know what will be the limitation of the heat pumps in terms of outdoor air temperature. Just a quick reminder here, every time you look at heat pumps, there are different considerations, and there's actually many more than what is shown here, but typically what's quite important is make sure you've got the electrical capacity before you start evaluating how to integrate it into your BAS, integrate it into your building, or even going into red screen to evaluate the savings. And the supply water temperature. You can have heat pumps that have plenty of capacity, but often the limiting factor will be what are the supply temperature you need to meet the load of your building. That can be the place where the heat pump will fail the test if it cannot provide the temperature that are needed for your building. And we'll get back to that because that is one item that when you start adjusting your BAS for the heat pumps need to be taken in consideration in actually quite great detail to get the best out of your heat pump system.
Michelle,
now, like I said, you need to integrate that into your BAS. Every time you've got a heat pump, you don't want to be an island. You don't want that to be standalone.
So, Michelle, we actually have one question.
Yeah, go ahead.
Yeah, it says back in slide 7.
Yes.
So the COP and capacity curves for the air heat pumps, why does the actual versus theoretical line show very different slopes?
Well, it's because manufacturers test under steady state conditions, whereas heat pumps, as soon as you have a heat pump, if it short cycles because of actual transient of the performance of the system, the transient behavior is never as efficient as the steady state. That's why, in general, you see the distinction between COP and performance because of those non-steady state conditions you have in real life compared to manufacturers' lab testing. So you got to be very careful about manufacturers' data. They're always under steady state condition. Just like a boiler will lose a lot of efficiency due to short cycling. Heat pumps, depending on how you control them, will lose efficiency because they are always more efficient under steady state, which is often not achieved for long periods of time in actual buildings.
And then we have one more quick question.
Yep.
Is replacing a boiler with air source heat pump and a water loop heat pump technically making a cascading heat pump system?
So I got the first part here. So can you repeat the last part of that question?
Is it technically a cascading heat pump system if you're to replace a boiler with the air source heat pump?
No, it's not. So cascading heat pump system is really you will have an evaporator, a condenser, and then another evaporator that's using that condenser as its source, and it's going to boost it up to a higher temperature. So if you only have one set of coils, so one condenser, one evaporator, that's a straight heat pump. Cascade definitely means you will have two sets of those, and those machines will actually feed one another to boost the temperature higher. As soon as you've got cascade system, keep in mind that the overall COP will degrade. So it's really when you want to use a heat pump and you need high temperature. You need higher temperature than a single stage heat pump will be able to provide, which typically would be around 135 to maybe 160, and that's pushing it. Anything higher than that, you will need specialized heat pump, cascade heat pumps, and you will suffer a COP penalty. So you've got a heat pump, or you're considering a heat pump, you want to integrate it into your BAS. Quick overview, your BAS is likely a 4-level system, or 4-layer, as you see here. You want to make sure that your heat pump has a field level controller, which typically we would call an ACC, and it's an advanced application controller in BACnet terminology. You want to select a heat pump that will be BACnet compliant, and it will have what's called an AAC. I said ACC, I'm sorry. AAC, an advanced application controller. It resides on what's called the field level controller of your BAS. It will give you much greater optimization opportunities. The number of points, and I'll show you an example that you can get out of an AAC controller, is really large. So you don't have to pay for multiple points on your heat pump if you've got a BACnet compliant controller. And like I said, will reside on this field level controller. So you'll be able to find your panels. You see where it's going to connect. So it's really good. If it's not a make or break, but it's really helpful to have a BACnet compliant AAC controller. So like I said before, you don't want your heat pump to work on its own. It will have multiple drawbacks if you do that. It will still give you savings. Your heat pump, you've got a rooftop unit that works on its own with its own controller, it's still going to provide you savings. But if it's integrated into your BAS, it will allow you to control the total building demand. It will allow to control any supplemental heating in a more optimized fashion. So the number of benefits really outweigh usually the cost of making sure it is connected to your BAS. Obviously, if your BAS is not BACnet compliant, you can always get something that's called gateway, which is kind of a translator between the OEM controller, the original controller from the manufacturers, and your BAS. But you really want to stay away as much as possible from those gateways, which are really translators for your machine that you bought and your BAS. In terms of the number of points that you want to have as a minimum for your heat pumps, they're very standard. I mean, a heat pump is basically an air conditioner working in reverse. So there's nothing that I can tell you that is not already something you should know, other than maybe the 4-way valve and the status of the heat pump. Is it in heating mode? Is it in cooling mode, defrost mode, and some are heat recovery mode if you've got a VRF or if you've got a 4-pipe heat pump. So the points are pretty standard, but you will add, like I said, the status, the mode, and if at all possible, make sure you get live building demand, because it will become a control point in a lot of your control strategies. What does it look like when you have the points on your BAS? Well, you see the very standard points for an air source heat pumps here. Those are BACnet compliant. So I'll show you what happens when you have a BACnet compliant controller. The number of points you can get becomes really, really large. Obviously, this is for one manufacturer. There's tons of different other manufacturers that will provide you as many points as you can see here on this BACnet compliant controller for a given type of water source heat pump. So like I said, make sure you've got those points available to you. Make sure you test them. I don't have that example, but communication is key. When you integrate a BACnet controller, make sure communication is fully commissioned and tested. There are lots of points available, but they need to be, the integration needs to be properly commissioned. Here's a summary of the main points that you would have if you had a BACnet controller. So let's assume, so you've got your BAS, you've got this BACnet controller, you've got your standard points as we saw before: supply temperature, supply water or supply air temperature, the status of the heat pump. You want to optimize now this control strategies for your heat pump. So some key elements that need to be considered when you start optimizing your heat pump. First of all is what is the operating range of that heat pump. So until when is it worth running that heat pump? You could decide to follow the manufacturer's recommendation. That means basically leave it to the OEM controller. What is way better is to know what is the heat pump capacity and what is the COP at a given temperature. There will be a point where, because of the energy rate, if you've got supplemental heating, you are better off not using your heat pump and using your supplemental on a cost basis. So you need to know, do I optimize on cost? Do I optimize on GHG reduction? So you need to have clear objectives. When you look at your BAS control optimization, it's not just about how do I better control the system, is what are the objectives? Because a heat pump can provide you savings very often all the way down to 0 degrees Fahrenheit or minus 20 degrees Celsius, but at a cost. There will be an energy cost, there could be a demand cost. So you need to have clear goals. Usually that's decided at, let's say the administrative level of the building. Who decides that? You need to know your rate structure, both for energy and demand. If you evaluate the impact of your heat pump based on a average or blended rate, it is a huge mistake. You never evaluate your heat pumps based on a blended rate, because your heat pumps will save energy but can create an excess demand. So when you start programming your BAS, those need to be known and taken into consideration, as well, obviously, as what is the efficiency of my supplemental system, because it may also vary with outdoor temperature, which is pretty rare, but it can vary with load. If it's fully loaded compared to not fully loaded, you can lose a lot of performance on that supplemental. So those are items that need to be known. People will usually program the BAS fairly blindly for heat pumps. They'll say, well, if it's minus 10 and below, I just stop the heat pump. They do not look at, do I optimize based on, my cost savings? Do I optimize on GHG savings? They just go with manufacturer's specs. Obviously, as you see on the slide, for air source heat pumps, you need to have an idea of how that heat pump, both capacity and COP, will vary with outdoor temperature. If you look at this graph, the graph at the bottom here, you will see that you can actually kind of predict what is your heating load. Heating load for a building will typically vary fairly linearly. So will the cooling load, and those are approximate. And you can actually have a crossover point where your heat pump will no longer be able to provide you enough heating. So that can be one item that goes into your BAS programming. You say, at this temperature, I know, let's say in this example, at around 16 degrees Fahrenheit outdoor temperature, the heat pump will no longer be able to meet the load. So now you know at what point you will need supplemental heating. It doesn't tell you how you're going to control it, because that will depend, is it a water source? Is it an air source? Then you will program your BAS depending on the heat pump. Say, it will be a hybrid operation where both heat pumps and my supplemental heating will work at the same time. Or you may have to go purely supplemental and turn off the heat pump. And again, this is a decision that will be based both on technical aspect, and we'll see why, and on economic aspect, depending on how much it will cost to keep running that heat pump at lower and lower temperature. So it is not a straightforward answer, but you need to consider both the COP, the heating capacity, and the energy rate that's applicable to the different source. But before you do that, on your BAS, you need to make sure that before you start programming the switchover, that your loads are reduced as much as possible. The lower the loads, the more you're going to get out of your heat pump system. The heat pump system is usually capacity constrained, so you want to make sure that this load is as low as possible. So before you start, integrating and programming the control sequence, review all the other control sequence. Make sure that you are optimized. You could do, the recommissioning, you could do a BS optimization prior to jumping into integrating the BAS. That typically would be a mistake. It's trying to throw an efficient system, which is a heat pump, at a very inefficient operation. So you're trying to compensate waste by an efficient system. This is a recipe for poor economics for your heat pump system. So, for example, ventilation systems reduce the airflow to the minimum required. You can use the man-controlled ventilation, and that depends on your type of ventilation system. You've got a VAV system. A VAV system is a poor candidate for the man-controlled ventilation for most buildings because they're cold deck system with only 10 to 15% outside air. So you've got to be very careful on how you will control that. What will be really important, even more than the ventilation system, is avoiding excessively high temperature settings. So you don't want to have excessively high space temperature, excessively high supply temperature for your hydronic loop, for example, because the heat pumps, not only are they capacity constrained, they are also temperature constrained. So you got to be very careful about minimizing as much as possible both space temperature and do not ever compromise comfort. So I'm not saying put the temperature in the space at 18 degrees. That's a mistake, but don't allow 24, 25, 26 degrees in heating unless for some obvious reason it's in your building, it's mandatory to have that. And do not always supply your hydronic loop at 160 and above unless it is required because you just get high temperature zonal heating equipment. So you got to be very, very careful about minimizing all of that. Obviously, if you can also reduce the load such with very simple low cost measure, because here we're not talking about high capital improvement to your building, but low cost, so reducing infiltration, trying to reduce stack effect by sealing the any exfiltration in the high part of your building, and making sure you do not get simultaneous heating and cooling. So once you've got that done, you've optimized the rest of your BAS so that your building, the needs is actually as low as possible. There's no inefficiencies. It's hard not to have some inefficiencies, but now you can start knowing what your actual building needs will be. And by talking about building needs is what is the actual supply temperature if you got a hydronic loop that is required to meet the load for a given outdoor temperature. In most buildings, you will see boilers have outdoor air temperature reset. And those resets are based on very often rules of thumb. People use that in building X, the same control company goes in building Y. They use the same reset. You should not do that. If possible, you should test. You do what's called a functional test, where you will test your building distribution system. Let's say it's minus 20 outside. You're going to try to distribute at 140. Does it meet the load? If it does not, you'll try at 150. And you see, this is not a simple procedure. It's a procedure that actually, the procedure is simple, but it is time consuming because you need to establish what is the true need of your building in terms of supply. And that could be supply air, can be typically supply water temperature, so that you know what is needed from your heat pump, from your heating system for a given outdoor temperature. This is how you will be able to maximize the use of your heat pump. Because if you use your old reset and you had a boiler system and you always distributed at 160 and above because it's a non-condensing boiler, you just killed the benefit of your heat pump because heat pumps will not distribute for the vast majority of them at 160 and above. So you need to know how low can I go? And when I say how low can I go is for what outdoor air temperature. There are systems, BAS systems, that can provide you that almost automatically, but be very careful about that. They often do not, they have their automatic optimal start, automatic optimization. It doesn't always work. If you use what's called the man reset, so the man reset, instead of being based on outdoor temperature, you will look at all the different valves, the heating valves in your building, and if they're all partially closed, that means you're supplying too hot because all the valves are partially closed. So for a heat pump system, if you can use the man reset, it is great, but you need to also know in the man reset what is the maximum temperature I need to provide. So you would do a similar test, but using demand reset is often, if applicable, if you need a fully DDC system, preferable, and it's called trim and respond. If you want to know more about it, you can always Google trim and respond. You'll see there's a ASHRAE guideline 36 that will provide you a lot of details on how to use demand reset using what's called trim and respond. And for programming your BAS for a hydronic heat pump system, definitely would be the way to go. And you don't need to have the heat pump to run those tests. Like if you've got a boiler, obviously if you've got a condensing boiler, it's easier. But if you've got a boiler, you can still run the test. You just have to be very careful if you got a conventional boiler system, so atmospheric boiler or non-condensing boiler. And if it's not a primary secondary loop, you cannot go below about 145. Otherwise, you may condense in your boiler. So you can run the test, but be careful. But that is what you need to do, because once you know the temperature limits, most heat pumps, you will also have their operating map, and they will tell you what is the temperature that can be provided by that heat pump. In this case, it's for an air source heat pump. It will give you the outdoor temperature. I forgot to put the axis at the bottom. It's outdoor temperature. So you got the outdoor temperature, and it will tell you what is the supply temperature that can be provided. And that's a different thing than capacity. So in heat pumps, always think, you look at your BAS, there's two items that will need to be considered. What is the temperature, the outdoor temperature, and then what will be my maximum supply temperature, and what will be the capacity, which will go down with outdoor temperature. Those two items will determine when you need your supplemental heating and when you need to possibly cut out your heat pump system. So those are the items you need to know, and they are available. Manufacturers will be able to provide you with that information. So once you've got that, so you know how low you can go with your distribution system, you know what the temperature of your heat pump can provide. Now you will optimize the operation of your heat pump and the use of your supplemental heating, other than if you have geothermal, where you often will not have supplemental heating at all. And as I said before, you need to have your goal. I always tell people, when you optimize a BAS, you optimize to a goal. If you don't have a goal, you basically don't know what to do, because you can't optimize without a goal. So if your goal is to maximize your, I say, economic benefit, or sometimes it's actually reduce to a maximum the penalty of running a heat pump system to still obtain GHG benefit, but to minimize your cost penalty. Sometimes it can be also a cost benefit. So typically what you want to do is to program the BAS so that the demand is known at all time, and you will run your heat pump until a time where either the outside air temperature goes below the manufacturer's recommended minimum value, where it will actually cut out, and you will go fully to your supplemental heating. But very often, this is not what's going to happen. You will run your heat pump, and as the demand goes close to a maximum limit that you set on the BAS, let's say 1,000 kilowatt, and you see that your heat pumps are coming on, and now you're at 980, then your supplemental heating will come on and will work in conjunction with your heat pumps to maintain the peak to a maximum of 1,000. And actually, it can be very close. You can get really good control, and until you have to turn off the heat pumps, but you will have this hybrid operation. We'll see that there are limits to that, because you can have hybrid operation as long as you're within the acceptable range of temperature for the heat pump. So for an air source heat pump, that's usually not a problem. An air-to-air heat pump, because the building air is never really warm, so you can always have that air-to-air heat pump work in conjunction with supplemental heating, and they can work both in tandem, and they can control to a specific demand. That's really what you would like to do to optimize for cost efficiency in many, many instances. That also means that if you did not integrate your heat pump into your BAS, you will never able to do that because the OEM controller does not know what's going on in the building. All it knows, it's typically the outside air temperature. So you will not be able to do that. That's why the integration is so important. If you've got a hydronic heat pump, so if you've got an air to water or water to water heat pump, and you put supplemental heating at the same time, now you can get into conflict where the boilers, which are typically the supplemental heat source when you've got a hydronic system, may be set to provide too much heat into that loop, raising the return temperature beyond what the heat pump can take, and it will shut down your heat pump. So when you are an air to air, usually you don't have that problem. When you're air to water or water to water, you can run into that problem. So you got to be very careful in actually commissioning your control sequence so that your supplemental heating, when it works in hybrid mode, does not turn off your heat pump due to high temperature. Uh, Obviously, you can control also based on outdoor temperature. As we saw before, you know your building load. We saw that the building load has a curve. Your heat pump has a capacity curve. You know where there will be a transition from the heat pump having enough capacity to not enough capacity. And based on that outdoor, I'd say, switchover point, you can start your supplemental heating. In this case, you do not have peak demand. Let's say it's a case where you do not have access to peak demand. You want a simpler method of controlling. You can control based on that switchover point where you can run hybrid, or you could go, depending on the economics, fully supplemental heating. And the same things will apply in terms of if it's a hydronic system, if you go hybrid operation and you work on outdoor air temperature, you will still have to be very careful on how much heat you put in with your boiler in order to ensure you don't trip your heat pumps in hybrid operation.
Michelle,
So
sorry,
yeah,
we have about 30 more minutes before our Q&A session.
okay, very quickly, a hybrid operation, we already talked about it. I said you've got to be very careful when it's hydronic because what you can end up with is something like you see on the screen. What you don't see on the screen is where there's this plate heat exchanger. On the other side, there's a supplemental boiler. It was set to supply at 70 because they did not revise the control sequence properly. They kept the old reset, and that ended up with a return temperature that was way too high. We have a return of 65, and that heat pump tripped and kept tripping all the time, which eventually can lead to a failure of that heat pump. So this is an example of improper programming of your BAS when you integrated the heat pump. You want to have typically hybrid operation is what you want. Going on off on a heat pump is usually not the most efficient way of using it when you have supplemental heating, which is most of the case. So you got to make sure what it looks like when you have this hybrid operation based on demand. You'll have something like that where you have your original profile where the orange line is the gas usage, the blue line is your electric profile. You will actually try to flatten that electric profile by controlling that hybrid operation on your heat pump to render that profile as flat as possible without exceeding a predefined set point, which will obviously maximize the use of your heat pumps on an economic basis. It will still give you lots of GHG reduction. And depending on your energy rate, and those are actually fairly old, so the rates that were used to do that calculation have changed for Class A and Class B. But for a heat pump, you may get benefits for both Class A and Class B. It depends on the energy rate and the COP of your heat pump. So if you got, like I said, if you can control demand to a maximum, you will never suffer a demand peak. So you can only use the energy rate, not the demand rate, to do that calculation. And Red Screen can help you along if you want to do those calculations. But again, your BAS needs to be programmed accordingly. And you need to know both COP and capacity at a given temperature. That will allow you to both program the BAS and get those savings. Once you've got that done, you've got your control strategy all defined, properly programmed, properly commissioned. There's other aspect of your controls that needs to be considered when you have heat pumps. Like I said, heat pumps are capacity constrained. So if you do setback, and by the way, setback always saves energy, but if you've got a heat pump, it could be costly because heat pumps have lower capacity. They have longer warm-up periods in most instances. So very often you need to make sure that if you were doing setbacks, you now have a heat pumps. You need to test, can my heat pump recover in the same period of time that my boiler did without creating a peak? Because if you say, I'm going to do a setback and I'm going to start at the same time, your heat pump won't be able to meet the load. Your supplemental heating, if it's programmed properly, will come on, because if the BAS sees that the heat pump cannot meet the load, it will actually call on the supplemental heating to come on. So now you're meeting your pickup time, your pickup heat, using the inefficient source, which would be your boiler, instead of using your heat pump. So you need to re-establish a new schedule for your night setback. And sometimes that schedule will actually modulate based on outdoor temperature. If it gets really, really cold, your setback will not be as deep because your recovery period would be too long. So really, really important not to just blindly use what was there before in terms of set point control. And because a lot of those heat pumps can provide both heating and cooling at the same time, the other thing that needs to be really, really well defined is separate heating set point, separate cooling set point with dead bands, so that you will not get an overlap at any time between heating and cooling, and you will not get short cycling. So for any system that can provide simultaneous heating and cooling, or where the mode can change from heating to cooling, make sure you have separate set points and that there are proper dead bands so that you avoid short cycling or simultaneous heating and cooling. Very quickly, I'm not going to spend much time on here. If you want to go further, you've got your BAS program, and like you said, it's many things to take into consideration, and you want to go even further to optimize your heat pump system. You can use what's called a model-based predictive control. There are actually a control company that offer those, but they're quite fancy, and you need a model. The model is not like a physical model of the heat pump. It's usually a model of how the building behaves with the heat pump. It's kind of a regression model for those of you who are used to red screen and regression model, linear regression of your utility use with outdoor temperature. Those controller use those kind of models to predict how your heat pump should be working given the forecasted weather, and usually the day of the week. If it's a Monday or a Wednesday or a Friday, the system will learn through that model, through that regression model, how the building will behave and how your heat pump should be set up and your supplemental heating. This is a quite advanced control. You do that really once your system is running and you're very comfortable with it. And usually you want a package, a commercial package that has been tested. The other one that's available, it's kind of similar. It's called model-free control. As the name says, there's no regression model. There's no model to try to predict. It's learned behavior. So it's really AI-driven. You can get neural network. You can get fuzzy logic controller. There are very few of those available, but that would be, again, one step further in optimizing your system. And this system will learn from how your heat pump system behaves. So it will need to be taught over time what is the good behavior of your system, and eventually it will optimize the system on its own. It's kind of way out there, but it's something that's in the future for optimized control of any system, but definitely for heat pumps. When I told you about cycling and the question we had, why do you don't get the actual performance that the manufacturers tell you? Very often it's due to transient and poor control. What you see here is an example of what happened with poor programming and poor commissioning of a 4-pipe air source heat pump system, where you had multiple change of operation many times in the day, which is horrible in terms of performance. And that was all because of improper programming and commissioning of the BAS. So you need to make sure that you trend, especially for systems that have multiple mode of operation. This type of system has 4 or 5 modes of operation, can result in heating, cooling, and then heat recovery mode, and then defrost, and then back to heating. So you got to be very careful. Last 5 minutes, I'm just going to tell you about FDD. Because heat pumps, just like chillers, air conditioner, are more complex, you usually can get more benefit of an FDD because very often the faults may not be as obvious as for a boiler. So you may benefit more on FDD for those more complex systems. So the FDD itself, as you know, has 2 real big portions. There's the fault detection, so they will gather all of the data. They have rules in there. Some of them have a little bit of AI, just a little bit, and they will spit out reports, which are the diagnostic. And in order to do anything with an FDD, you got to work on the diagnostics. So you get those diagnostic reports. If you do nothing with them, you might as well not have the FDD. And the FDD is only as good as the sensor data that is going to collect. So you need to have the proper points. If you've got a AAC, so a BACnet Advanced Application Controller, you'll have tons of points. So your FDD will be much better than if you only have the supply and return temperature and is the heat pump on or off and in which mode. That would really limit the FDD. So I'd say if you don't have a lot of internal points from your heat pump, don't go down the route of FDD right now. You better improve the number of points by having, like I said, an AAC with a lot of points before you jump into FDD. Otherwise, it would be a waste of money and a waste of time. Some example that you can look at later on for FDD. So the FDD can tell you for an air source heat pump, is it overcharge, undercharge, is there liquid line restriction? Like I said, a lot of those would be very difficult for the operation team to diagnose really quickly. Whereas if you've got sufficient point, the FDD will be able to tell you those kind of possible faults. But like I said, it will be possible faults. It will still rely on the operating team to make sure that it got it right, because very often it gets it wrong because it's not sure exactly what is the issue. It suspects that's what it is, but sometimes issues can have more than one cause. So you got to make sure that your team is well trained into that FDD and how to act on the FDD. More example of diagnostics that can be provided by your FDD, evaporator fouling, condenser fouling. Some of those are pretty obvious, but some of them are not as obvious. And that's why it will really help on the long run if you've got sufficient point to have an FDD. And like I said, you see at the top here of this graphic, it says operational personnel. They are key. An FDD where the operational personnel is not well trained and well versed into FDD is a waste of money because those reports will sit on a desk and will do nothing. Most FDD do not correct the situation, will not interact with your BAS. Some do, most don't. So you do rely on that operating personnel to be able to take those proactive action and those action. And make sure that if you do go with an FDD, you have a good maintenance program for your BAS, because an FDD relies on your sensor. If your sensors are not reliable, the FDD is gonna keep spitting out reports for failure that are just sensor issues and not actual failures. So make sure you got a good maintenance program. And usually what I tell people when I provide the recommissioning course, I say, don't take a company service contract for granted. They say we will calibrate all sensors every year. That's not true. There's no companies that will calibrate all sensors on the BAS every year. That's just too expensive, too long. So instead of having this contract that provides you with this generic sentence, we'll calibrate sensors, establish with them a list of the critical sensors. What are the critical sensors for your BAS, for your heat pump? And those need to be calibrated. And then you can get reliable reports from your FDD. you'll get less reports and they will be more accurate diagnostics. So your team will not lose confidence on the FDD because they get so many reports that are wrong. So this is actually a very critical part of having an FDD. And like I said, it's applicable to any HVAC system, but is even more critical for heat pumps given the complexity involved in having a heat pump. And just an example of what an FDD could, and actually anybody could, but an FDD could provide you diagnostic about startup. I told you if you got setback with a heat pump, you can kill yourself with demand costs because it's going to be way too high. As you see here, we kept getting morning spikes, and that was bad heat recovery. The FDD, if that point is on your BAS, would be able to provide you that feedback if somehow it was not seen by anybody else in the building. So I know we went quite fast, lots of stuff to do. The one thing I want you to remember is you're looking at heat pumps. You need to know what type of heat pumps you're putting in. You need to know the limitations of those heat pumps. And then what are the requirements of your building? Your BAS will not guess those. You cannot use rules of thumb for those. When you have a boiler, you can actually get away with using rules of thumbs because boilers have usually excess capacity. They are not limited in temperatures. You cannot afford to do that with a heat pump. You want to get the most out of your heat pump, you need to optimize your overall control sequences, then program your heat pump control sequence with that in mind, knowing their limitations, knowing what this building needs, and obviously the rates. You got that, you will be able to program your BAS so that your heat pumps will work the most for you, get the most benefits on GHG and cost reduction possibly, or limit the cost increase. And last layer, if you want to get some good diagnostics, you can have an FDD as long as you've got sufficient points, and those points are calibrated, at least the one that you consider critical. And I know I kind of went fast there, but we do have 2 minutes if there's any other questions.
Yes, I do see 3 questions in the chat right now. The first one is it a good practice to install heat pumps with gas backup?
I consider it to be a very good practice because if you go with heat pumps on its own, especially air source heat pumps, and you don't have a backup, there will be time where you will run out of capacity. You could decide to go with an electric backup if you really want to decarbonize, but then you will not be able to limit your demand. The demand will go up significantly because of that backup. So usually at this stage of where we are in electrification, a air source heat pump with gas backup is usually the optimal in terms of practical, let's say, practical aspect, reducing GHG and minimizing your cost increase.
And then I see another BS related question. It's a pretty long one, but I've observed that some manufacturers, even though they have a backnet card on the heat pump, many of the points requiring control from the BS do not provide read or write options to fully integrate into the BS. The OEM controller, in most cases, control the sequence of operation. What do you suggest to address this issue when more control is required for the BS?
Well, usually those points, when they are not read or write, they can become, I mean, they are blocked by the manufacturers. So you could decide to go with a different manufacturers because they are accessible. It's a decision that they make not to make those available to you and to limit your ability to control. And if, for example, that limits your ability to do hybrid operation, you would need to either install new points to control that, which would be expensive, or just don't select that product because you need to be able to do that fine tuning to get the most out of it. So either they unlock those points for you, or you go to a different manufacturers, or you can actually take over the control. But there's an significant additional cost to that.
I do have one more question. It's non-BS related, so I'm gonna ask if anyone has any BS related questions for the heat pumps. I know we're right on time, 11 o'clock. If there's any other questions, please feel free to raise your hand or ask in the chat. Okay, we do have a question. Yes, Curtis? I think you need to unmute yourself.
Is that the Curtis that I know?
There. Are you able to talk now?
Yes, I'm able to
Yeah.
talk. Hey, Michelle, good to see you.
Hey, Curtis, how are you?
I'm good. I'm good. It's been a while. Yeah. You're looking fresh. That's good. Um, yes. I just wanted to raise a point. Let's say we have a few rooftop units that are gas fired, old, obsolete now, needing end of life replacement, right? And we've decided to, and this is a case where, from experience, we decided to replace these rooftop units with heat pumps. But what came up as something that was not even considered was the fact that the weight of the heat pump is more than the weight of the rooftop unit that was there prior, requiring the need to look at
Structure?
enhancing your roof structure, um, which came at a cost that was not necessarily envisaged. So I just wanted to raise that point.
Curtis, did your previous rooftop have cooling in there?
Yes.
It's surprising. Usually, yeah, there is a slight weight difference, but usually a heat pump rooftop unit versus a gas rooftop unit. Yes, you do have the supplemental gas, I would assume that's still there, but the heat pump is really just an air conditioner with a four-way valve, so the weight difference is typically not enough to cause that. But I'm surprised that in your case it did.
Yeah, it did. And it's just something that I just wanted to raise that, whenever you're looking to do those kind of replacement, it's important also to look at your roof load capacity. And again, what came up was that there was a requirement to have a smoke detector, within the duct, and as part of the whole operation of the unit for in the event of a fire, for example, that it would have triggered a shutdown of that unit. Unfortunately, the unit that we acquired didn't have the ability to have that smoke detector installed and integrated. And again, there was also the need to look at some, changing the size of the duct, which created a lot of little issues and additional costs for us.
So I'm going to take a wild guess here because the weight question that you raise is usually not a problem because, like I said, a heat pump is just an air conditioner, and if you had a 10-ton and you replaced by a 10-ton, the weight difference should be very little, and the duct size usually, and not usually, all the time, ducts are sized for cooling purposes. So is it possible that they upsize those units, let's say from 10 ton to 15 or 20 tons, and that explains both the duct size issue and the weight issue? Because duct size is usually not a problem when you go from gas to heat pump because the duct is sized for cooling, so it's way sufficient for heating, even for a heat pump.
Yeah, no, they did not. It's
They
just
did not.
no, it was based on the capacity requirement.
Okay.
So that didn't happen. But what happened was that the building itself was actually a building that was somewhat old in terms of the existing infrastructure.
Okay. That's so maybe even if you had gone to natural gas, those ducts may have been judged to be too small because they were going back. They were going back to code maybe for that
Yes.
building. Yeah.
Thank you for that question. Is there anyone else with any questions before we wrap it up? I know we're over the time. Okay, we do have one non-BS question. If you can answer that quickly, and then we'll wrap it up. This one's from David. It's how much HVAC load is lost through windows, and what about the secondary window options like panels that now have coatings for both heating and cooling?
Well, windows in terms of heating, hi David, as you know, they are the largest portion of the building envelope heating load. So typically, I'm trying to remember here, it's like maybe 40% of your heat goes out through windows. So obviously, if you can improve the windows to reduce the load in the winter for the heat pumps, it's a huge deal because it's your number one heat loss element. And usually, depending on how much ventilation you have, it could be the largest heat loss parameter of the whole building for a lot of buildings. So anything you can do at a low cost to reduce glazing losses would be huge for allowing your heat pump to work more, to provide you more of your percentage of heating.
Thank you, Michelle. With that being said, I think we'll wrap up here. Reminder, this
Sorry, just
Yeah.
one more thing, and Michelle raised this point. The use of the FDD is something that can, of course, support the whole optimization of your heat pump and your BAS. But one of the things also to consider from again experience is the need to ensure that the sensors and the FDD is actually somewhat of a separate system, so to speak, that has to be maintained and properly monitored too, right? It's like you gotta be cognizant that your FDD and your BAS, are gonna be sort of working together. But if you have problems with sensors failing on your FDD side, then it's going to be not necessarily as effective. The other thing is FDD on new equipment might not be as useful as on older equipment, right? So that's something that I think we should probably maybe you could speak a little bit more on that if what I'm saying is correct.
Oh yeah, yes, you're correct. Like I said before, the sensors, your FDD will be really deterred by bad sensors. You will lose a lot of time because of that, and because new equipment. You're right. New equipment, because it's new, should have very few issues. The issues will be more with the commissioning of usually the equipment. So it can be beneficial in helping catch some of the commissioning mishaps, if I can say, that happen with new equipment. So it's still beneficial for new equipment, but if you've got old equipment, you are going to obviously get a lot more diagnostics of possible failure. But don't, because of commissioning issues and how commissioning sometimes is skipped, the FDD can be beneficial even for new equipment.
Thanks. Yeah. All right.
Thanks.
Love the presentation, Michelle. Let me know when you're in my area of the woods.
Yeah.
We could
All
probably get together.
Thank you, Curtis. And with that being said, we'll wrap it up. Thank you, Michelle, for an amazing presentation as always. And thank you, everyone, for attending. We do have more trainings and sessions coming up. So I think Michelle can go to the following slides.
Yeah.
They'll be on the Sale on Energy Training and Support section of the website. So please feel free to access that webpage, and then you can see more of our upcoming webinars and sessions. And yeah, thank you, everyone, for attending. Bye, everyone. Thank you.